Warning! Under U.S. law, it is illegal to make any device to suppress or reduce the noise level of a firearm, or to attach anything to the barrel of a weapon with the intent of reducing the sound of discharge. This is a major felony, punishable by many years in prison. The Bureau of Alcohol, Tobacco, and Firearms, the ATF, actively investigates and prosecutes those suspected of federal firearms violations. In order to avoid violation of U.S. law, portions of this video were filmed outside of U.S. territorial jurisdiction. The information in this video is presented for its informational, academic, and entertainment value. Do not attempt to make any of the devices shown in this video, or you will be in violation of federal law. In this video, we examine the principles on which firearm suppressors or silencers operate. The suppressors shown here were made with the use of machine tools, lathes and mills by this federally licensed manufacturer. But in this video, we will examine the fabrication of units like this one for the .22 caliber pistol. This device was made without the use of machine shop tools, using commonly available materials and simple hand tools. We then field tested these units using precision decibel meters and frequency spectrum analyzers. The results of these experiments were recorded and will be presented graphically. We will begin with a brief history of firearm suppressors. Born in 1869, Hiram Maxim is often credited as the father of modern firearm suppressors. The Maxim units used a series of baffles to cool and dissipate muzzle blast, thus reducing the sound of a gunshot. Here we see a bullet racing ahead of its own muzzle blast. It is these hot, high-velocity gases of muzzle blast that are the chief source of firearm noise. It should be noted that while now illegal devices in the United States, silencers were once popular items with turn-of-the-century sportsmen, as this 1922 Field and Stream ad testifies. This picnicker is shown with a Maxim silencer on his .22 caliber Quackenbush rifle. In fact, a former president of the United States, Teddy Roosevelt, was known to purchase and use Maxim silencers. The Maxim units attach to the customer's weapon by use of a special muzzle clamping device. Such muzzle clamping devices are available today through mail-order sources. Other devices which attach to the muzzle of a weapon, such as recoil compensators and flash suppressors, can serve as the base of an improvised method of suppressor attachment. The attachment method of the suppressor to the weapon's muzzle is critical. Any misalignment could mean the bullet might strike the internal baffles, blasting the device apart, which could injure or blind the shooter. In this next experiment, we deliberately misalign this dummy unit to show the result. The attachment method is critical because a misaligned suppressor constitutes an obstruction to the barrel. This could blow up the weapon and injure the shooter. We now examine improvised methods for attaching suppressors to the muzzle of the weapon. There is a great deal of literature available on improvised suppressors. A popular method in these books is the tape buildup method because of its simplicity and ease in attaching the suppressor to the muzzle. We experimented with the tape buildup method, but found it only acceptable for disposable suppressors, such as the one we see here, fabricated from a 2-liter pop bottle. A second method of attachment popular in the literature is what we call the split tube and ring clamp method. In this method, a metal tube slightly smaller than the diameter of the barrel is used. A channel is cut with a hacksaw or moto tool to allow the front sight to clear. The diagonal slashes you see in this barrel extension are to relieve the gases of muzzle blast. Additional cuts in the tube will allow it to slip over the barrel. A ring clamp will be used to secure it. Opposite the cuts, a grommet is slid down the tube. A PVC cap with a hole drilled to accommodate the tube is used. This provides a flush surface to epoxy the grommet to the PVC end cap. The barrel extension will be epoxied to the grommet as well, and a ring clamp will be used to attach the barrel extension to the barrel. The body of the suppressor will be made from a piece of PVC pipe which slips into the end cap. In the actual assembly, PVC cement will be used. The split tube and ring clamp attachment method can be adapted to many weapons using various size tubes. While quick and easy, we found two significant problems with the tape buildup and split tube ring clamp attachment methods. The first problem is that these methods do not ensure proper alignment. Each time the suppressor is removed and the ring clamp retightened, a different alignment is established. A misaligned suppressor is dangerous. The second problem is that these attachment methods are only secure enough for .22 rimfire weapons. Larger caliber weapons will likely blow off suppressors attached with either of these methods. What is needed is a more secure clamping system and a means to ensure proper alignment each time the suppressor is removed. An ordinary bicycle seat post clamp proved far superior to the ring clamp in holding power. The alignment problem was solved by using standard plumbing fixtures as the barrel extension, which were internally threaded. Let's take a look at the other parts of this assembly. First, the part we just saw slide into the bicycle clamp. This is the barrel extension, which will be cut to slip over the barrel. As purchased in a plumbing supply shop, it is an internally threaded part. The standard plumbing part you see here is threaded externally on both ends. This part will connect the barrel extension with the nut, which is internally threaded. This part will thread into the other end of the nut. Let's see how it all goes together. Again, a PVC end cap is used. a hole having been drilled in the center to allow the barrel extension to pass through. Note that this cap is threaded, as is the PVC suppressor body that will be used. A washer distributes the force of screwing down the assembly over the PVC cap. The barrel extension and outside threaded connector are passed through, and then the nut is screwed down, locking the PVC cap between the barrel extension on either side. This ensures correct and repeatable alignment. The rubber material of the bicycle clamp provides an excellent gas seal, and the clamp itself, when screwed down, provides a very strong attachment. Using various size plumbing fixtures and sometimes brass bushings, we found this method of attachment suitable for a wide variety of weapons. Threaded barreled weapons provide another alternative for suppressor attachment. Some weapons, such as this AR-15 rifle, come equipped with flash suppressors. After loosening with a wrench, the flash suppressor can be removed, exposing the threaded barrel. Gun steel, such as used in barrels of rifles and pistols, is generally too hard to cut with hand taps or dies. However, the soft brass bushing in this PVC end cap assembly was hand tapped using a common hardware store tap to match the AR-15 threads. The device you see here was not designed as a noise suppressor, but as a test chamber to allow daylight videography of muzzle flash, as we will see later. For weapons using removable barrels, such as the 9mm Sten gun, threaded barrels are available through mail order. This device is for the Colt Woodsman and requires gunsmithing to install. By far, the most satisfactory improvised method for attaching suppressors is the mail-order muzzle adapter. These adapters provide the benefits of a threaded barrel, perfect alignment, and repeatability, without any modifications to the weapon. Like the early Maxim couplings, each muzzle adapter is made for a specific weapon. This one is for the Ruger Mark II pistol. The machined unit is simply slipped over the front sight and then secured by tightening the locking clamps. This method allows all the benefits of a threaded barrel without any modifications to the firearm. We now examine just how a suppressor works. First, we can identify three sources of firearm noise. The first of these is simple mechanical noise. Mechanical noise is simply the noise of the moving parts slamming into one another. Revolvers cannot be effectively suppressed because so much of the hot gases escape between the cylinder and barrel gap. Suppressors have no effect on a firearm's mechanical noise. Muzzle blast is the second and most significant source of firearm noise. The hot expanding gases of the burning propellant drive the bullet down the barrel. When we hear a gunshot, we are primarily hearing these hot gases hitting the cooler outside air as they exit the muzzle. A third source of firearm noise is supersonic crack. A bullet moving faster than the speed of sound creates a mini-sonic boom, similar to a jet aircraft. To avoid supersonic crack, the bullet's velocity must be reduced to less than the speed of sound. There are only two ways to achieve this. One is to reduce the powder charge. This reduces the velocity of the bullet, but in some weapons the reduced powder charge does not cycle the action reliably. The second method of achieving subsonic bullet velocity is to port or drill holes in the barrel to reduce its efficiency. The hot gases escaping from these holes will be trapped by the suppressor body, which slips over the barrel. Porting a barrel requires machine tools to be done properly. An ordinary hand drill would destroy the weapon's accuracy. Let's examine another relevant effect of a bullet moving faster than the speed of sound. This graph shows how a bullet loses velocity, measured in feet per second on the vertical scale, as it moves downrange, measured in hundreds of yards on the scale at bottom. The flat blue line represents the constant speed of sound at just below 1,000 feet per second. Note that at about 600 yards the graphs intersect, and the bullet is now subsonic. Observe that after the bullet has gone downrange 250 yards, its initial velocity of 3,300 feet per second has dropped to about 2,000 feet per second, about twice the speed of sound. The velocity of the bullet continues to drop till at 600 yards, its speed is below 1,000 feet per second, roughly equal to the speed of sound. From this point on, the bullet is not moving supersonically, therefore no sonic crack will be heard. But at such a distance, the sound of the shot, its decibel level, has dropped dramatically as well. We conducted these field experiments to demonstrate these effects. Notice that the only sound recorded is the impact of the bullet itself, not the sound of the shot. After traveling 570 yards, the bullet is moving at subsonic velocity, so there's no supersonic crack. The camera does not record the sound of the shot at this distance. Let's watch again. The drop in decibel level and the loss of velocity, which occur at long range, almost amount to a natural suppressor effect. This is why military snipers most often do not use suppressors when firing at great range. Since a silencer or suppressor only affects muzzle blast, let's examine this phenomenon more closely. The hot gases of muzzle blast result from the burning of the powder, a chemical propellant in the cartridge. Consequently, the amount of muzzle blast is directly proportional to the size of the cartridge being fired. Bigger cartridges need more propellant and thus create more muzzle blast and noise. At far right is a high-powered rifle cartridge and its powder charge. At far left are 22 rimfire cartridges and their powder charge. In this next experiment, the device was constructed to allow videography of the muzzle blast of this AR-15 rifle. Observe. The prime function of a suppressor is to cool and reduce the velocity of these hot expanding gases. Let's now examine how this is accomplished. A perforated barrel extension, which can be simply rolled up screen, allows the hot gases to escape into the baffling material. Often, this material is steel wool. This cools the gases as they transfer heat to the steel wool. Next, baffles strip more of the hot gases from the bullet. The spaces between the baffles allow the gas to further expand and thus cool. A rubber wipe completes the job of retarding the hot gases from freely exiting the muzzle as the bullet exits. The following computer animation depicts this process more dynamically. Suppressor designs vary somewhat, but this one is typical. The hot gases first hit a large volume chamber, allowing them to expand. When a gas expands, its pressure drops, as does its temperature. Steel wool or copper scouring pads are often used in this chamber. Sometimes lithium or white grease is added to the steel wool to further cool and dampen the gases. The bullet then passes through the baffle chambers, while much of the hot gases are left behind. The gas that does pass through expands in the spaces between the baffles. Finally, the bullet exits into the outside air after passing through a hole in a rubber endwipe. The hole in this rubber endwipe is only slightly larger than the bullet. This creates a partial gas seal. In order for you to appreciate the performance of the improvised suppressors we will demonstrate, we need to know something about decibels and frequency. Observe this field test. Both weapons are firing the same .22 long rifle cartridge. The first weapon has been suppressed by a major Class III licensed manufacturer and is clearly much quieter than the unsuppressed weapon. However, to the observer present, the difference in noise level is far more dramatic than the audio track of this videotape can demonstrate. The decibel meter shown here measures the intensity of sound. What is needed is a familiar frame of reference of the decibel level of common sounds. This will allow you to compare the noise level of these familiar sounds with that of our improvised suppressors. This TV set, at normal volume, registers about 48 decibels. The volume is then turned up all the way and the instrument recalibrated.
El América 1, Veracruz 0. Lo anticiparon a Del Olmo. De Veracruz, Poblete está solo por el medio.
At full volume, the TV registers 56 decibels. Dropping the book directly in front of the sensor, 69 decibels. The balloon pop in front of the sensor registers 74 decibels, but if we move the balloon back just 3 feet, the decibels drop off dramatically. We will be examining decibel drop-off over a distance shortly. Move back just 3 feet, we get a register of 66 decibels. The pellet gun registers 64 decibels. This .22 pistol registered 110 decibels. We will be using the following graph as a baseline of comparison for the noise level of our improvised suppressors. Recall how sharply the decibel level dropped at a distance. Our common sense and experience tells us that things happening further away don't sound as loud. But let's examine this relationship between sound level and distance more closely. The green line represents the drop-off of bullet velocity, the pink line the constant speed of sound. The blue line represents decibel drop-off at a distance. Note that at the muzzle, the weapon registered 180 decibels, but after traveling 550 yards, its sound level has dropped to about 20 decibels. Recall our field experiment. Disposable suppressors are just that. Recall our 2-liter pop bottle suppressor shown earlier. The ballistic nylon catches the .22 caliber bullet. This unit registered 77 decibels, a drop of over 30 decibels, using subsonic ammo. This pistol fires the .22 short cartridge at right. The .22 long rifle at left is shown for comparison. This tennis ball provided the disposable suppressor for this diminutive cartridge. It registered 54 decibels, about the same as a loud television set. The 2-liter bottle shown earlier achieved its silencing effect by providing a single large expansion chamber for the muzzle gases. The tennis ball also provides a superior gas seal, as the first shot creates the exit hole. Though good for only one shot, the power steering bottle dropped the sound 16 decibels. We now examine the construction of improvised suppressors. Our first unit is designed for the .22 caliber pistol. The body of the suppressor is made from ordinary 1-inch steel electrical conduit. It is cut using a pipe cutter. This achieves a flush, smooth end. Standard 1-inch grommets will provide our baffles. These grommets fit nicely inside the 1-inch steel conduit and are therefore self-aligning. Sometimes the grommets will require a little bit of grinding to achieve this ideal fit. The 1-inch steel conduit at top is 1 inch inside diameter. The aluminum tubing below is 1 inch outside diameter. This means that the aluminum tubing slips inside the 1-inch conduit. The aluminum tubing will provide spacers for our grommets. The standard 1-inch grommets thus fit flush and even with the 1-inch aluminum spacers. Brass tubing is also available in 1-inch outside diameter. In this first design, a piece of brass tubing will be used as a barrel extension. This tubing has the same outside diameter as the holes in the grommets. Cuts are made in the barrel extension to allow the gas to escape into the dampening materials. A high-quality epoxy is used to attach the grommets to each end of the barrel extension. A piece of steel screening is cut the length of the space between the two grommets. The steel screening is then wrapped around the barrel extension. Rubber bands are used to temporarily hold the screening in place. The screen is then secured with metal twist ties. Using a technique of the Class 3 manufacturing pros, white lithium grease is added to the screening material. This will help cool the hot expanding gases. A small piece of screen is rolled up and inserted into the aluminum spacers as well. It expands, providing the bullet path. In the actual assembly, lithium grease would be used on this screen as well. Let's examine the main components of this assembly. First, we have the nut epoxied into a end cap, followed by the barrel extension relieved to allow the gases to escape. Next come the aluminum spacers. Between each is a grommet. At the end, a rubber wipe. The first bullet will cut the hole through the rubber wipe. An electrical conduit end cap will complete the assembly. These electrical conduit end caps snap fit into the 1-inch conduit. This first design for the .22 caliber pistol will make use of the commercially available muzzle adapter couplings shown earlier. A nut with threads that match the muzzle coupling is epoxied to the inside of the electrical conduit end cap. A hole is cut in this end cap just large enough for the muzzle threads of the adapter to pass through. The standard nut fits nicely in the end cap. In the actual assembly, it will be epoxied in, and the hole will be larger. The end cap is coated with epoxy and then tapped with a hammer to seal the unit. A wooden dowel is used to aid in the assembly of the suppressor. First, the barrel extension, followed by the aluminum spacers and a grommet. Note that the grommets are inserted pointing in towards the muzzle of the weapon. The spacers are stacked with a grommet between each spacer. With the aid of the wooden dowel, the entire assembly can then be inserted into the 1-inch conduit body. The wooden dowel is then removed and the final rubber wipe inserted. In the actual assembly, the end cap will be epoxied on. A coating of flat black paint, and our unit is ready to test. Units of this type design register approximately 70 decibels. Note that at 71 decibels, our .22 conduit suppressor is a little bit louder than the book drop and a little quieter than the balloon pop. Our second unit uses a PVC suppressor body. The nut has been epoxied into this smaller piece of PVC tubing. In the actual assembly, this part would be inserted with PVC cement to secure it to the suppressor body. In this design, a barrel extension is not used. A piece of metal screening is flattened out and the steel wool spread and pressed against its surface. A wooden dowel is used to roll the steel wool up in the screening material. The screening material will be secured with a piece of copper wire. Our 1-inch OD aluminum spacers used in the previous design will be used here to cap each end of the screen and steel wool assembly. This will allow this assembly to be inserted into the PVC body more easily and will also align the bullet path. Removing the wooden dowel, we can observe the bullet path. In the actual assembly, the aluminum spacers would be epoxied. The entire assembly is then slid into the PVC body. The PVC body has an inside diameter of 1 inch. The wooden dowel is used to recheck bullet path alignment. A grommet is added, which secures alignment, and a small rubber washer in preparation for our final wipe. Our final wipe will be cut from this thick piece of rubber. A piece of the PVC tubing will be used as a template. And the wipe simply cut out with scissors. The rubber wipe is inserted inside the PVC end cap. The first shot will establish the bullet path through the PVC wipe. The PVC end cap containing the wipe is then pressed over the PVC body. In the actual assembly, this part would be secured using PVC cement. The PVC cement makes a very secure and easy hold. However, it makes a permanent installation. The caps cannot be removed to replace parts of the suppressor. This design proved more effective than our conduit unit shown previously. This PVC unit registered 63 decibels, slightly louder than the pellet gun. The unit was also longer and thus had more internal volume, but the use of screen instead of a cut barrel extension likely accounts for the superior performance of the PVC unit. The bottom line is that how loud something sounds is quite subjective, being interpreted by the brain through the sensor of the human ear. There is more to how loud something sounds than simply decibels. This graph shows that the ear is not equally sensitive to all frequencies. Inside the yellow line is the range of human hearing. Inside this, we have the range in decibels and frequency in the range that music occurs. Note that the speech region has a maximum decibel level of about 80 dB and a frequency range between 100 and 8,000 hertz. At a loudness value of 40 decibels, a sound of 50 hertz is audible. However, at a frequency of 500 hertz, the sound becomes audible at only 10 decibels rather than 20. Past 10,000 hertz, the ability of the ear to hear a sound drops off very rapidly. The human ear is most sensitive to sounds between 500 and 5,000 hertz. This is the frequency region that suppressors reduce decibel levels the most. In general, a suppressor shifts the peak decibel level to the higher end of the frequency spectrum. We now examine our final and most successful suppressor design. This unit uses the bicycle clamp and plumbing fixture attachment method. The body of the suppressor is made of 3 1/2 inch inside diameter PVC pipe, which comes threaded at each end. The end caps are also threaded PVC. This unit is larger in internal volume than the previously demonstrated 22 long rifle units in order to handle the greater amount of hot propellant gases of the 9mm cartridge. The 9mm cartridge is shown here. To the left are the 22 long rifle, and at far left, the 22 short. Here we see the primary components of this assembly. A piece of PVC irrigation tubing will be used as spacers. The PVC end caps are threaded to match the PVC body. Steel wool will be used as a diffusing material, and metal washers replace our grommets as the baffles. Once again, the outside diameter of the spacer material matches the inside diameter of the suppressor body. The spacer material must be cut flush. A piece of screen is wrapped around a dowel and secured with wire. This is inserted inside the spacer. The steel wool is then forced around the dowel and screening. The dowel provides alignment. Removing the dowel, we can see the bullet path, which is made about 30% larger than the 9mm slug. A second piece of screening is slipped over the barrel extension, which has been drilled to allow the hot gases to escape into the packing material. The screen keeps the packing material out of the bullet path. Let's examine how all the pieces go together. Again, a wooden dowel is used to aid in the assembly. First, a baffle chamber is inserted. The succeeding baffle chambers will force the ones before it to the end of the tube. A steel washer goes between each baffling chamber. Another steel washer. And another baffling chamber. Rubber washers are used to fill the space at the very end of the tube before the final end wipe is added. These provide a gas seal. In the actual assembly, the end cap would contain a number of similar rubber washers. Using the bicycle clamp and plumbing fixture attachment method, the unit is locked down to the barrel of the weapon. This device suppresses muzzle blasts so well that the mechanical noise of the weapon becomes discernible. In this field test, the decibel reading was made at a distance of 15 feet from the shooter and therefore cannot be directly compared to the previous tests. A reading of 57 decibels was registered. This improvised suppressor test is more suitably compared to the following field test of another 9mm submachine gun, a Mac 11, using a Class 3 manufactured suppressor. In this test, the decibel sensor is also set approximately 15 feet from the shooter. Both weapons are firing the same 9mm cartridge. The Mac 11 is clearly louder. In fact, this Mac 11, using a suppressor made with the benefit of machine tools, registers a whopping 79 decibels. a full 22 decibels higher than our improvised unit. Part of this difference is attributable to the fact that the Mach 11 is lighter and naturally louder than the British Sten gun, suppressed or not. It also has a higher cyclic rate of fire. However, these tests do demonstrate that improvised suppressors can sometimes equal or even exceed the performance of machine tool units. A firearm suppressor works much like an automobile muffler, which cools and baffles the hot gases of an internal combustion engine before they exit the tailpipe. Likewise, a suppressor cools and reduces the hot expanding, higher velocity gases produced by the burning propellant of the cartridge. Machine tools provide the ideal solution to both the alignment and attachment problem and can use metal rather than flexible rubber wipes due to the precise tolerances machine tools can maintain. Without the benefit of machine tools, improvised suppressors must use rubber wipes. These burn out fairly quickly and affect accuracy since they often touch the bullet as it exits the wipe. Machine tool units are thus more durable and can be made so precisely that the bullet never touches any internal wipe. This makes machine tool units more accurate, but as we have demonstrated, improvised units can be just as quiet as the best machine tool manufactured units. Finally, though silencers are portrayed in the movies as instruments of spies and assassins, no suppressor is so efficient that the shot cannot be heard nearby. The reality is that suppressors were once popular items with sportsmen and target shooters simply because, in reducing noise and muzzle blast, they make firearms more pleasant to shoot. Remember, U.S. law has made firearm suppressors illegal. Do not attempt to make any of the devices shown in this video. This information is presented for the benefit of persons with an interest in firearm science and who just want to know how things work. I hope you found our video entertaining and informative. Thank you.